In Triple Alpha, we have three programming languages: Hydrogen, Helium, and Beryllium. They let you program at different levels of abstraction. Beryllium is our object-oriented programming language, sitting one level above Helium. Where Hydrogen expresses code at the gate level using structured control flow blocks, and Helium introduces a familiar, basic-like syntax for that control, Beryllium provides the full richness of a high-level language for writing complex quantum programs. It offers a rich type system, C-style control flow, functions with typed input and outputs, user-defined modules, and object-oriented programming constructs like classes. In this video, we will show you how to write a program in Beryllium. Every Beryllium program starts with a main function, which is the entry point for execution. Functions let you reuse blocks of code. You define functions outside main with the func keyword. A function has a name, an optional ordered list of input parameters with their data type, an optional output type, and a body wrapped in curly braces. The name, input parameters, and output make up the function signature. Two conventions to call out. First, the return variable is declared in the signature's arrow parenthesis block, not in the body. Inside the function, you simply assign a value to it. A plus mesh1 minus mesh2 is assigned to the output variable b. Second, a function can return only one value. To return more than one, you bundle them into a struct, which we will see in a later section. These examples show three common shapes: a function with both inputs and output, a function with no inputs but an output, and a function with inputs but no output. In Beryllium, the return variables for functions are optional. Notice how the first two examples have a return variable, while the last example has inputs but no return variable. You call a function by its name, passing inputs as arguments. If the function returns a value, you assign it to a variable of the same data type. Beryllium supports recursion, so a function can call itself. Here, we define the function flipQubits, which applies an X gate to each qubit in an array by recursing on a shrinking index. Return exits the function immediately, which is useful when you want to exit early. Finally, Beryllium also supports function pointers. These are references to functions that you can store in variables, pass as arguments, or hold in arrays. We won't cover them in this video, but they are documented in detail on the function pointers documentation page. Beryllium has a rich type system. There are two primitive data types: numeric and quantum systems. From these, you can build composite data types, including arrays, structs, and classes. Beryllium also supports function pointers, which let you store references to functions and pass them around like values. The numeric type stores integers or real numbers. QSys with a dimension parameter declares a quantum system with the dimensionality of your choice. You initialize it using an initialization command from your instruction set. For example, the qubit command initializes a two-level system. An array is a data structure containing elements of the same data type. To declare a one-dimensional array, append a pair of square brackets to a data type. To access or assign an element, write the array name, a dot, followed by the index in square brackets. Beryllium also supports multi-dimensional arrays. Each pair of square brackets adds another dimension. A struct is a user-defined data type. Its purpose is to group multiple fields of the same or different data types under a single name. Informally, a struct organizes data like a composite structure, but in Beryllium's type system, it is itself a data type. In this example, we use a Grover struct to package the data you'd need to run Grover's search algorithm. It contains arrays of search and ancillary qubits, the search qubit count, the number of iterations, and an input parameter array. You instantiate a struct inside main by declaring a variable of the struct's type, then access its fields using dot notation. Beryllium supports numerous arithmetic operators you would expect in a C-like language, including addition, subtraction, multiplication, division, modulo, and exponentiation. We won't cover this in the video, and you can learn more about this as part of our documentation. Beryllium supports if statements, for loops, while loops, and switch statements for controlling program flow, all of which can be nested if needed. You can also use jump statements like break and continue inside loops for more complex logic. This is an example of a classical if statement, branching on a numeric variable. Conditions occupy the first pair of curly brackets and the body in the second. Here, we measure a qubit and apply a different gate to a second qubit depending on the result. We also support quantum if statements. This example branches on a qubit variable. When the condition is on a qubit rather than a classical variable, the if becomes a quantum if, and the operations inside are coherently controlled by that qubit. For example, applying an X gate to Q2 is a C0, a controlled X gate with Q1 as the control and Q2 as the target. A for loop has 4 parts in its own braces: initialization, condition, increment, and body. For loops are commonly used to populate and process arrays of qubits and measure qubit results. Inside a loop, continue skips to the next iteration, and break exits early. Both can be placed behind conditional if statements. A while loop consists of a condition and a body. A while loop runs its body repeatedly until its condition is broken. A module is a Beryllium file, .qbe, containing reusable functions that helps you organize Beryllium code across files. You can import a module into another Beryllium file to access these functions. There are 2 ways to import a module in Beryllium: importing the file directly or importing the file with an alias. To call a function from a module, use dot notation with the module name or its alias. Here's an example. This example packages an inverse quantum Fourier transform routine, IQFT, into a module called QFT helper and calls it from main.qbe with a 6-qubit array. Each file must explicitly import every module it depends on. Files cannot directly access nested modules. If main.qbe imports module A and A imports module B, then main can only access A directly and does not automatically get access to B. Beryllium is an object-oriented language. A class is a data type that acts as a blueprint for creating an object. It defines the properties and methods of an object. An object is the individual instance of a class. Declare a class with the class keyword, followed by the class name, and a body, containing 2 blocks, properties and methods. The properties field declares the variables stored in your object. They can be accessed by class methods. Methods are the functions within a class. The methods field contains the class constructor, a method whose name matches the class name, and the class methods. A method's first parameter is always the object the method is called on, and it has the same type as the class. In this example, the parameter is called self, and the name itself has no special meaning in Beryllium. When you call a method using .access, the instance is passed automatically as the first argument, so you leave it out of the call. Instantiate a class by calling the class constructor and assigning it to a variable with the class type. To call a method on the instance, we use .access, pair.prepare with no arguments. You can group multiple instances of the same class into an array of classes. This is useful for managing a collection of related quantum objects. In this example, we store 3 instances of the class state with different theta values, initialize a 1-dimensional array of type state, store the 3 state objects in this array, then iterate and call prepare on each stored value. A child class inherits all the properties and methods of a parent class. This avoids duplication and lets you build families of related objects. The left arrow operator indicates inheritance. Beryllium supports single inheritance, from parent to child, and multi-level inheritance, from parent to child to grandchild, and so on. Multiple inheritance, where a child inherits from multiple parents, and cyclic inheritance, where a parent inherits from its child, are not allowed. A child class can override any inherited method by declaring a method with the same signature. A signature is the same when it has the same name, number of parameters, parameter types, and return type. Here, a GHZ triple class inherits from its parent bell pair. It adds a third qubit as a new property, defines its own constructor so that all 3 qubit gets initialized, and overrides prepare to produce a 3-qubit GHZ state across all 3 qubits rather than a 2-qubit bell pair. Calling GHZ prepare runs the overridden method, entangling all 3 qubits. With classes, inheritance, and overrides, you can build a small library of reusable quantum objects and compose them into bigger programs. You've now seen how Beryllium brings familiar programming constructs, such as typed functions, classes, modules, and reusable libraries, to quantum programming. By giving you classical and quantum building blocks that compose into richer, higher-level structures, Beryllium lets you focus on what a quantum algorithm should do, rather than the low-level details of how it's implemented. To learn more about writing in our programming languages and the instruction set, please refer to our other videos. Happy coding!